Good, good, good. Right. Don't want to forget that.
So how many people do we have in now?
There's 12 at the moment.
Right.
So we probably want to wait a few more minutes for people to join in.
On my screen, Clemens, I can see George there. I'm glad he came. And if you want to sort of hit on him for some color information, although I doubt you need that.
Hi, George.
Hi, folks. Sure.
With us tonight.
Glad to talk if you have questions.
Yeah, so many questions about the color on topaz. Unfortunately, the reasons are mostly physical and not chemistry related. So this is a problem I have with the topaz color.
Yeah, it's a little bit of both. Radiation especially is a very
Yeah.
important factor.
Yeah.
Gonna touch on this a little bit, of course. We have to in the blue topaz.
Mhm. Oh, yes.
Well, our
Antoinette
friend
is
from
also here.
Florida used the original cyclotron to turn the topaz blue. I was gonna try and get him, but I thought, you know what, I don't want to dilute Clemens' message. We still have another few minutes.
Hi, Charles.
Julian, how old is your son now?
He's 7.
Well, that's a great age.
Yeah, we went to a mineral show today.
You went to the
there's-
mineral show?
Yeah, a little mineral show at Oxford.
Yeah.
So we didn't stay very long there because it was quite small. One of the things that's interesting is that everything is going towards fossils. Fossils are the big thing now. There were 50% of the dealers were fossil dealers, and they were the ones getting most of the interest.
Is he starting to get interested in rocks?
Oh, Roman. Oh, yeah, he is. Yeah.
Good.
Mm,
Got to pass along those genes and activate them.
yeah. Mm.
Well, in the meantime, I can play a little bit around with my topaz specimen to show you all what we're talking about today. Huge ones.
It looks
and
like a
colorful
micro-
ones. Yeah, it looks a little bit like a helmet here.
Is that Pakistani?
That's a Pakistani piece, yeah.
Yeah, it looks like that sort of association group. And has it faded at all in all the years you've had it?
Actually, I'm just having it for a couple of weeks or months
Oh,
right
it has a
now,
good-
but the
the
piece
color
is
has a
old.
good lifetime yet.
It is something like almost 20 years ago.
Yeah.
Yeah, I got it from a friend of mine. It was one of the first mineral shows, and I said, "Oh, I like this, but I can't afford it." Now he said, "You know, it's available again." So this time I got it.
Well, that's good when that can happen.
The second large piece from this find is in the museum in Milano, so it's very prominently displayed.
And what are we up to now, Julian?
We are 31 participants, and it is now just gone past 8 o'clock. So over to you, Ray. Well, you can start whenever you are 32.
Can we give
or
the
you wanna-
stragglers 5
Yeah,
minutes?
give it, yeah, maybe, yeah, a few minutes for people to come in. Probably should ask everybody now, except the next speaker, to mute themselves, at least, would be good. And I shall mute myself as well, and I will now hand things over to Ray to take control.
Well, first of all, I'd like to welcome everybody for showing up today. It's in some places the weather is horrendous. Back at my home, we're having floods and horrible disaster area. And so I decided to run away to Jamaica. And so I'm broadcasting from a place near Duncan's, Jamaica called Silver Sands. And so I'm sort of enjoying the few moments I have here of sunshine. Where I live, sun hides most of the wintertime. So this is our 13th program. We're now over a year old. And our 13th program focus, as you probably already know, is topaz. And so interestingly enough, I found that topaz has always been an interest of mine, and it used to be great because when you could go down to the big shows and get good quality large topazes for pennies on the dollar, it was exciting stuff. But nowadays, that's changed, and the mineral guys are buying the crystals that used to be thrown in the direction of the cutters. And so we're seeing a lot more of the original crystals being saved. And as a mineral collector, I'm exactly thrilled to know that and happy that that's happening. We've lost too many great gem crystals to the cutters.
Oh.
No offense meant, Clemens, but and I'm just as evil as the rest because I've had stones cut where I probably shouldn't have. Long and short, I was privileged to know Charlie Keyes back in the day when Bill Pinch brought him up from Florida to a special meeting he had at his home in Rochester. And Bill was renowned as a mineral guy, but equally renowned as a gem guy as well. And so this was a gem meeting that he was holding, and Charlie Keyes told us about his original experiment, because he'd heard that possibly, I'm sorry, I don't want to steal too much of your thunder, Clemens, but that stones could be affected by radiation. So he asked someone in the local cyclotron to throw a few of his almost valueless white topaz in and see what happened to them, and sure enough, they changed color. And we'll hear more about that later from our one and only and amazing guest speaker today. And it's not often, well, he is amazing. It's not often we only have one speaker, but sometimes when you got the best, you just take what you got. And today we're having one of our former speakers coming back and joining us again. And I really like that because he's one of our better speakers. And his name is Dr. Clemens Schwarzinger, and he's an associate professor of chemistry at Johannes Kepler University in Linz, Austria. And his specialty is polymer chemistry plus scientific gemology. So he has a broad range of knowledge and interest. And he sullied his reputation by having been a mineral collector for so long, but gem people will forgive him for that. And I think from what I just saw a minute ago, he still is a mineral collector. And people who are lucky enough to go to the Munich show were probably also fortunate enough to see a portion of his topaz collection, for which he's known to be somewhat passionate about, and maybe even a little bit obsessive about his interest in topaz. And that sort of makes him one of the leading, if not the leading, topaz expert in Europe and the world. And also, to make it even more interesting for me and some of you, he's also an award-winning gem cutter. And those of you who are privileged enough to see his showings online every once in a while, you see these amazing, beautifully cut, perfectly cut stones done by someone who really knows what they're doing. So not only does he know the science of gemology, but he knows how to translate that into the cutting of the stones so that the light that you look for and the color you want is prominently displayed in the best possible way. So without any further ado, I'd like you to welcome Dr. Clemens Schwarzinger, who's going to share with us tonight, or today if you're in the more westerly areas, his knowledge and his experiences around his passion for topaz. Dr. Clemens Schwarzinger.
Thank you very much for this kind introduction. Actually, I'm looking for somebody else standing behind me who is all these experts. So I'm just a small cogwheel in all this huge industry and in all these, among all these passionate collectors and scientists here. So I just want to give you the short invitation on this huge chapter of topaz. And as it is such a huge chapter, I decided more or less to take my collection and give you a couple of my pictures and to show you what I have done recently or in the last many years. And now I want to show you also my slides. So the topic today is topaz. Topaz, you all know, is the birthstone, or one of the birthstones for November. And I myself was born on the 9th of November, and a couple of other people here in the audience are born in November as well. So this is our stone, and therefore maybe this is the connection that I have to topaz. I don't know why I started to collect topaz, but at the end I'm stuck with topaz, and I try to get my hands on almost all types and colors. Also, it's not that easy anymore. Some deposits are long gone now, and it is hard to find specimens from there, but still I'm trying more or less hard. So if this works, yeah, I need to move some things here away to see the slides myself. So this is what typically people are thinking about topaz. You have these blue gemstones, dark blue. Yes, it's typically a cheap gemstone. In this case, it's not such a cheap gemstone because it was cut by Stefan Kotlovsky, who was also a great master facet, unfortunately passed too early. And the other thing that people are knowing is, yes, topaz, that must be these huge crystals, like this 0.5 meter size here in Vienna. We have also huge ones in many other museums. Many of those are even gem quality. So you do find them in all sizes and in all qualities, but they are known for these huge crystals and for typically the blue color you find in, I will call it, cheaper type of jewelry. So what I'm going to talk about today is a little bit of the chemistry and the crystallography. Of course, we need to understand a little bit of this one. Colors are important, natural colors. And if I say natural colors, of course, there must be also non-natural colors. We have treatments, irradiation, heat treatments, sputtering. And if we talk about treatments, we also have to look at the gemological side. How can we detect those treatments, or is it possible to detect treatments at all? And we will have some pictures of minerals as well as gemstones from different occurrences. Gemstone, topaz, of course, all over the world, almost everywhere except the country I'm living in. We just had one find of topaz, and the largest pieces are about 1 centimeter and 1 or 2 millimeters in diameter. But everywhere else, almost, you can find the topaz. And finally, I'm going to conclude with some science stuff that's for a couple of you in the audience, but at least should be interesting and entertaining for everybody else as well. So what is topaz? Where does the name come? What is the gem? Usually, what have people thought of to be topaz in the past? There are a couple of theories. One is, for example, that the name is derived from the Greek topasios, which was the name of an island in the Red Sea, also known as Sabarjat or as St. John's Island. And there have been gemstones found there, or minerals found there, and they have the color of fresh oil. They mean olive oil, I'm guessing there. So they have this yellowish greenish color, which we know now is peridot. So peridot is found in St. John's Island, has nothing to do with topaz, but at least the name might come from this island. And the other theory is that it comes from the word tapas, which means heat or glow. And it should describe all yellow stones, because at the beginning, 17th century, something like this, many topazes that were found and identified were yellow, like the famous European ones in Schneckenstein Cliff in Saxonia in Germany. These yellow stones have been used for jewelry for a long time. So the question, what is topaz, can be answered today rather easily. We have chemical analysis, and we know that's different colors. However, where the name comes from, not 100% sure. What we do know, however, is what is not topaz. Like the trade name smoke topaz has long time been used for smoky quartz, and also Madeira topaz has been used for citrine, both quartz varieties, which are easily to distinguish from topaz. Now, looking at the chemistry, we're talking about an alumosilicate. So we have 2 aluminums, we have 1 silicon, we have some oxygen, and we have fluorine and hydroxyl groups. And here is single difference in all the topazes is the content of fluorines that we have. It's not like tourmaline or garnet where you have lots and lots of different elements that play major roles. So topaz is a rather pure crystal with not a high number or not high values of other elements that are incorporated in the crystal lattice. So looking at the crystal structure, we have here the tetrahedrons, which have in silicon in the core and 4 oxygens at the corners. And we have the octahedrons with aluminum in the core, with 4 oxygens at the corners and two corner points where we can have either the hydroxyl or the fluoride ion. 2 of the octahedrons are connected to each other via one edge. And from the points, we have the connection to the silicon tetrahedrons, and those are building up these 3-dimensional structures. So we have the C-axis going from the top to the bottom. We're looking here in the direction of the B-axis. And what we have here and what is very typical for topaz is 90 degrees to the C-axis, we have a perfect cleavage plane. So this is one of the problems with topaz. It is very hard. You see here we have a hardness from the Mohs scale of 8, sorry. But the problem is if you ding it in the right direction, it will break along the cleavage plane. And therefore, also, if you look at the mineral specimens that are available, you will have many, many single crystals, but only rarely you have matrix pieces because they just break off the matrix easily. So for the gemologists, we need a couple of numbers to be listed. The density is 3.5 to 3.6 gram per square cubic centimeter per cubic centimeter. This is similar to diamond, which is interesting because a lot of time, if you're in the field, you get offered a diamond, which proves to be just a carefully cut topaz. People try all the time. The refractive index would give it away in a second because we have 1.61 to 1.64, and we have a double refractive of 0.01. So what differences can we find in topaz crystal? I told you already, it is the difference between fluorine and hydroxyl. We can have completely 100% fluorine on the positions, and we can have an exchange of up to 30% hydroxyl in this fluorine. So we have more or less not 2 complete end members, but we have one end member that's the fluorine topaz, and we can have an exchange of this fluorine up to 30% for hydroxyl. And what is the outcome of this exchange? The more hydroxyl we have, the lower the density becomes because the group is more bulky, it stretches the lattice, and therefore we have a higher volume. And what is interesting for gem cutting is we get a higher refractive index. So the more hydroxyl groups we have, the higher the refractive index is, the better the cutting properties are for a gemstone. The coloring elements in topaz are not that many because we have chromium, vanadium, which are known to cause a pinkish to orange, or actually a pinkish to red color. There are a couple of topazes that have been proven that are free of chromium, but have manganese and some iron inside. These ones are from the United States. And also the manganese seems to have the tendency to color the topaz in pink. But in most cases in topaz, we have lattice defects. So we have some holes in the lattice where some elements should stay, or we have some trapped oxygen atoms. We have oxygen with strange oxidation states or not typical oxidation states. And these lattice defects, they cause most of the colors in topaz. They cause the yellow, they cause the brown, and they cause the blue. Of course, topaz can be formed in different ways, and this is also something that we can relate to the shape if we know the crystal and also the color or to the physical properties. For example, hydrothermal occurrences, which are Ouro Preto in Brazil, Sanarka in Russia, or Katlang in Pakistan, those crystals can easily be recognized because they have elongated growth. We have slender crystals, and they have this high refractive index, therefore they sparkle a little bit more than the other ones. And those are the ones that we often find under the term imperial topaz. We'll come to this later and maybe have some huge discussions on where the name comes from or what is imperial topaz. Then there have been rhyolitic occurrences like Zacatecas in Mexico or the Thomas Range in United States. But most of topaz is formed in pegmatitic localities. So this is the ones where we have the huge crystals, clear crystals, a lot of gem material, but with the high fluorine content. Well, topaz is known for its size, as I already mentioned a couple of times. So the largest cut gemstone is a topaz. Here we have the El Dorado topaz, 31,000 carats, which is the largest conventionally faceted gemstone in the world. And here's a nice photo of Chip Clark. And if I'm correct, this is the daughter of Shane McClure here, sitting here. So it's not a new photo, but these two topazes are in Washington, the Smithsonian Institution, and the American Golden is number 3 or 4 in the largest gemstones, still 22,875 carat. So this is nice, something to play with. And you know, these gemologists that are always crawling on the floor and looking for the gems they just lost in the tweezers. If you have the right topaz, that doesn't happen. You just hurt your toes, for example, if it falls on your feet. Now let's talk about the colors. We have to start with the color that is mostly associated with topaz. This is blue. So we have blue topaz in nature, which is typically a light blue. If you cut them, they lose most of the color, and compared to a dark blue stone, they look more or less colorless. I can assure you this one is a light blue color. And we have this irradiated topaz. I'm always asked, if you see this topaz, can you analyze that it is natural or that it is synthetic color or artificial color? And in most cases, I can tell people, just look at it. You see it with your eyes if you have the experience that this color has never been found in nature. So you can find this irradiated topaz, this typically dark blue topazes, as faceted stones, but you can also find them as crystals. So even the crystals are put into red reactors or neutron sources or whatever you can think of, and produce these dark blue colors. Another color that is very much liked is this orange color from Brazil. Ouro Preto is the one source that has really made this material famous. If you're lucky, then you have some red reflections here at the ends, but in general, you have crystals or gems that have this dark, intense orange color, and this is what people typically refer to as imperial topaz. However, these topazes can also intensify color, and if the chromium content goes up, they can become pink to even red. And also red cut stones are available, like this one here in the Fields Museum in Chicago. This crystal is in my collection. You can have very rarely natural green stones. So green is possible in nature. You don't see it very often. However, also with radiation treatment, you can produce green colors. But this radiated green color is not very stable. And we have a lot of yellow, of course, yellow Ouro Preto crystal here, and these yellow faceted topazes. Not to speak, of course, of the colorless, which is the majority of all topaz crystals. Now, what causes these colors? I already told you in the beginning, the majority is the color centers. Color centers is more or less the incorporation of ions with different charges that cause holes. So you might remember from your basic chemistry classes, even in high school, everything needs to be neutral in order to be balanced. So if we incorporate an ion that has a higher oxidation state, like the one that should be sitting on this place, we need to make up this charge difference. And this can, for example, be done by oxygen or by single trapped electrons. And very often we have these trapped electrons, and these defects cause the yellowish to brown and the blue colors. Metal ions, unfortunately, are rather rare. We have the chromium or seldom vanadium that cause the pink to red colors. Very often it's hard to differentiate because whenever you have chromium, you do have a certain amount of vanadium. Typically, the chromium is in higher concentration than the vanadium, and the absorption spectra look rather different. So you have to look carefully to see the difference. And some rose red specimens have already been found that do not contain the chromium, but they have manganese and maybe some amount of iron 3, which typically causes yellowish color. But if you mix the two perfect colors, like we have the chromium, which is red, and some color centers, which are yellow, you get the orange, which Rupreto is known for. Now, if we speak of color, we need to address the irradiated topaz. So this is a perfect example of what I think a medium blue color. Very often you have these dark blue colors, which do look nice in small stones, but if you try to cut the larger stone, they look like a dark sapphire. So also irradiation does not produce the color that you like, but the color that the stone has more or less the history for. You can play a little bit around with the conditions of irradiation and heat treatment, but you will always have some stones that do not turn the color you like and some stones that do completely different things. So how can we design the color? Let's put it like this. In history, we have the first gamma sources which were used cobalt 60 emitters. And with these cobalt 60 sources, you can take a colorless topaz, turn it brown, and after turning it brown, you heat it to a temperature of around 200 degrees and it turns blue. So while this brown color is not stable, it can be returned to the colorless or more or less colorless state if you put your topaz into the sunlight. UV radiation, for example, is one of the enemies of the brown color. And the other thing is temperature. So you turn them to 200 degrees, they turn blue. If you heat them up to higher temperatures, they might turn colorless again. However, the difference between these two temperatures, where you turn them blue and you destroy the blue again, is so high that the blue color is considered to be stable. So whenever you cut it, you put it into jewelry, you wear it, this color is stable and does not fade with sunlight. The next step would be an accelerator where you shoot with electrons onto your sample. There you get some greenish to brown coloration, again heating to 200 degrees, and then you turn them blue. In this case, the trade name sky blue was used to describe this hue of blue. Next step would be a nuclear radiator. You shoot with neutrons on your topaz. Here you don't need any heating. They turn to the so-called London blue, a rather dark blue, and you can leave it like this. Or you can go to the nuke, then to an accelerator, and then heat it, and then you end up with the so-called Swiss blue topaz. So a couple of different possibilities. What they all have in common, they knock some atoms out of the lattice, some electrons come in, take the place, they cause some absorption in the UV ultraviolet visible spectral range and create this blue color. A couple of questions always come people to mind if they hear that topaz is treated with radioactivity. So is the topaz, the treated topaz, radioactive by itself? In general, you can say no. Why do I say in general? Because in general, if this is done in a proper lab, people know how to use their neutrons. You have to differentiate between two types of neutrons. We have slow neutrons, and you have fast neutrons. So the fast neutrons, they just shoot through their stone, they cause the color, and they leave the stone. If you have the other neutrons, which are slow, they have not enough energy to pass through the stone, so they get trapped in the stone, and then they can create radioactive isotopes. And this is what you do not want. So therefore, if people do know what they're doing, they block the slow neutrons before they hit the stones. Only the fast neutrons go through the stones, cause the coloration, and they do in general not induce radioactivity. However, if there is some radioactivity present in the stones are sent to cool off for a couple of weeks or a couple of months, and then they are sold when they're absolutely safe. Unfortunately, there are many sources around the world which are capable of radiating topaz and other minerals, and they're just doing it out of profit. Of course, everybody's doing it out of profit, but they want the quick money, and they don't keep the stones in the safe for a couple of months. They just sell them hot as they are, and then there is a chance that your topaz is radioactive. However, the amount of radioactivity typically is very small, and if you don't wear it all the day in front of some sensible part of your body, I would not take care too much about this. So in general, we can say, no, there is no radioactivity in the treated topaz, and therefore you can also not detect this treatment by just using a Geiger-Müller counter. There are a couple of techniques that have been proven valuable to identify this treatment, however. For example, thermoluminescence. If you have the influence of heat, the blue color can be erased. And you can record even a spectrum where you have the light evolution versus the temperature. You can create these profiles, and you can see difference between natural blue color and this radiation-induced color. The problem is that this test is not non-destructive. And this is one of the problems I always have with customers. They give you some stones and say, can you test it? And I say, okay, may I grind it in powder or may I dissolve it in the solvent? And no, please return it the same state that I gave it to you. So a couple of tests proved to be not eligible for these testing. Another possibility is absorption spectroscopy. Karl Schmetzer has found a couple of data that support the idea that we have blue to blue violet color centers that can be visualized in polarized absorption spectroscopy. Problem with these tests is always you need to test a huge amount of material from very different sources, compare them to another huge amount of natural samples to be sure that what you're seeing is conclusive. This, in my opinion, would be a very easy test. However, I could not repeat all of the results, all of these findings with the samples that I had in my hands. And another possibility would be gamma spectroscopy. So identification of radioactive isotopes with highly specific germanium detectors. So this is even if you do not see or do not measure the radioactivity with a Geiger counter, there might be some strange isotopes in the material that you can detect with costly experiments. And this is the major problem that we have. Most of these techniques that we can use to identify the treatment cost way more than the gem itself will cost. Because if we're talking about treated topaz, treated blue topaz, you can buy them for $10, $20 the carat. And analysis like gamma spectroscopy runs into the thousands of dollars. So if you go to court, okay, that makes sense. But if it's just to understand if you have a natural or a colored, a treated blue topaz, most of these techniques do not make sense. And even if they would make sense, not all work. So in my opinion, it's not possible to determine if something has not been treated. It's only possible to determine in some cases that a gem has been treated. So this is a big difference, especially if you're talking with a lawyer. So how can we be sure now that a piece that we have in our hands has natural colors? Is it natural or is it not natural? In this case, I was told, let's say it this way, this is a bicolored topaz from Volodar-Spolin, which is now called Koroshiv in the Ukraine. So how can I be sure if most of my analytical equipment fails to identify the treatment? Well, one of our guests here comes in. This is how I can be sure that some or many of my specimens are natural, because I know the guy who pulled them out of the ground here, Peter Lickberg, carrying a 30-kilogram topaz in the small smoky, and here from another pocket, which is called the gem pocket in Volodarsk, you see the specimens directly, freshly out of the ground. And if you have this, what I call the pedigree from the miner the finding directly to the mineral and to the cut stone, then you can be sure that there have not been any treatments done to your gems. But there is not only radiation treatment, there's also second treatment, which is very often done in Brazil. Why in Brazil? Because it is specific to this Ouro Preto topazes. Ouro Preto topazes do not only come in this wonderful orange or pink hues, many of them have this brownish coloration. And this brownish coloration is due to the fact that we have some pink due to the chromium, and we have some color centers, which cause the yellow color. And if you mix the yellow and the pinkish, then you get this orange in the best case, or some brownish like this. And now we have to understand a little bit of physics and chemistry, because we know that if you have an element like chromium that doesn't change by heating, it might change its oxidation state, but in case of chromium, it doesn't. It stays the trivalent chromium. However, the yellow color centers, which are distortions in the crystal lattice, can be erased by heating the topaz to higher temperatures. The lattice starts to vibrate at higher temperatures, and a lot of the defects dissolve into nowhere. Let's put it like this way. So you can erase the history of the treatment. So the yellow goes away and you're left with the pink. And therefore this process is also called pinking. And temperature of 500 degrees is not really something that you can detect like in the sapphire, where you heat sapphires up to 1800 degrees. You see some damage to the crystal, to the inclusions. This damage at 500 degrees does not occur, and it's almost impossible to detect this type of treatment. It is possible if you have the stone before and after the treatment. We did FTIR spectroscopy, we did Raman spectroscopy. You see a change in the hydroxide content. However, in the nature, you have such a huge distribution of possible abundances of peaks, so that it's not possible to say if you just get one specimen that it has been heated or it had not been heated. You might have some indications, but again, it's not really possible to determine this pinking here. So this is the problem that we have in the trade. If you see a pink topaz and if you see a blue topaz, you have to assume that they are treated, and this brings down the value. If you have a pedigree, of course, you can say, yes, this is a pink topaz. I found it in Katlang. I have cut it. It has been traded by this and this person. And you have all the photos and all the information. Then you can prove that it's natural color, and then it commands some extra prices. A wonderful treatment, because it's so obvious that it's not natural, is mystic topaz. So mystic topaz is nothing else than you have a cut crystal or a cut gem, and you apply a thin coating of either aluminum, gold, or titanium dioxide on, for example, the backside of your gem. And the size or the thickness of this coating is within the range of visible light. And therefore you get some diffraction. You have the light, part of the light is diffracted within the different layers of the coating. And then you see the colors of the rainbow on the front of your gem. If you try to remove it from the top, if it's a set gem, very often you don't see anything because the cutting is only on the pavilion. If you unmount the gem, it should be obvious. You just scratch a little bit and you see the natural skin or the natural facets of topaz coming through. Okay, let's talk a little bit about the occurrence of topaz. I told you already in the beginning, topaz can be found almost all places of the world. If you're lucky, you might find it if you dig in your garden, for example. But there are a couple of indications that help you to identify where topaz could be found. And this is, for example, a map of the rare earth elements, and also tin elements very often go together with the finding of topaz. So we have here we have Colorado, we have California, we have Utah here in the United States, we have Mexico. We have, of course, here in Maine, some findings of topaz. We have Spain, a little bit in Ireland, and here in Saxonia, we find some topaz. A lot can be found in the, or has been found in the Ural Mountains, and here in Central Asian parts. We have Pakistan, Afghanistan, Burma. We have Africa, of course, with Namibia. We have Nigeria here in the part. We have Brazil, and we have Argentina, and we also have Australia. So topaz can be found really almost everywhere, except for Austria, as I already told you. Greenland, I think they haven't found any topaz so far in Greenland too. So I cannot give you a list of all of the important places where to find topaz. I just decided to have a few of them, and I will walk you through my collection, part of locations I have to fill in with museum pictures. But let's just have a couple of pictures of cut stones as well as crystals, because crystals is always easy to identify. If you see the crystal, you can, from the shape, get some idea where it comes from. And if you have an idea where it comes from, you know what color it should have. If you have accessory minerals, everything makes it easier than just having the cut stone. The cut stone is always the hardest part to identify, and to identify location has become very, very interesting in gemology. Not only for sapphires, it's for garnets, it's for many other materials. Luckily, so far, nobody has asked where your topaz comes from, because it's simply too cheap. So we will have Brazil, we will have Pakistan, Afghanistan, Ukraine, Russia, USA, Nigeria, Namibia, and Myanmar, and start here with a nice 130 carat stone from hematita in Brazil. So Brazil, however, is more famous for the blue topaz. It does have some natural blue topaz, Lavra de Chanda, Itinga, Virgem de Lapa. There are a couple of occurrences where we have either crystals or eroded, corroded crystals. We have Nova Era, where you have a slightly greenish touch. So this was a new find in 2018. I bought a couple of pieces in Tucson in 2019. Wonderful material. Unfortunately, in the photos, they don't display the greenish tint very well. Look a little bit like blue. But Brazil is also known for the imperial topazes. So we have from this yellowish orange up to the red color. Here a cut stone from my collection. Unfortunately, I cannot help out here with a red one. Therefore, I borrowed this photo from Greg Polle. And this is one of the newest additions to the Smithsonian collection, almost 50 carats, the Whitney Flame. You very, very rarely see a topaz crystal or a piece of rough that has this wonderful color. And you can understand why people fall in love with material like this. Going to Pakistan, we have to discuss a little bit what we would expect. For example, here, this is typically pale brownish crystals. Also the cut stone, we have this pale brown. And then we have these orangey dark brown crystals. So for those who joined early, I had this huge topaz crystal, which was dark brown, but it was dark brown and had no orange tint. And if we think about the color, where does the color come from? So the brown color comes from displacement in the crystal lattice, from electrons being there. And the reason is radiation treatment. So this radiation treatment, we have learned, can be done by man, but it is also done in nature. We don't have cobalt-60 here close by, but what we do have is a lot of potassium. And potassium does have one radioactive isotope, potassium-40, that is not a very harsh irradiator, so it takes some time. So if you think about the history of the Haramosh Mountains and the Himalayan mountains, they are rather young. And if you have young mountains, so the formation of crystal is not too long ago, and the potassium-40 didn't have a lot of time to irradiate the topaz. So what you would expect is light colors, not this intense orange. And the second clue that we have is we have the quartzes here, which are jet black. And many people know the Arkansas quartzes, which when you dig them out of the ground, they're colorless, they're optically clear quartz crystals, and then they get irradiated. they have a certain amount of aluminum inside, then you get this black quartz. We have the black quartz and we have these dark topaz. So this is a very, very good indication that this material might have been treated. Also, nobody can ever tell you the truth about this. I have people telling me, yeah, we find this out of the ground, no question about this, but you will have a lot of other people who say, no, they have these light smoky quartzes, not the dark ones, and the orange is also not natural. The treatment is not easy to detect, therefore you have to assume a color or a piece like this to be treated. So if you have Pakistani material, most of it will be this light brownish, little bit yellowish color. And what they also have in common, most of them will fade when you present them to daylight, to the ultraviolet light. There are a couple of occurrences where we see stable material that has been out in collections for 20, 25 years, and it's still dark brown. However, many of these crystals fade with exposure to sunlight and therefore turn more or less colorless. But Pakistan also has another wonderful location where we can find topaz, and here we can see the elongated crystals which point us to a hydrothermal growth. And these hydrothermal topazes from Gundao Hill in Katlang, they are known for wonderful pink colors, and this one is not photoshopped. I can't believe me. This is a crystal of my collection. Both of them are, and this is really this deep pink that we have. I did cut a couple of materials, but unfortunately not this color. This is almost impossible to get by, and if it has some crystal faces, you have to pay huge amounts of money. So you will not sacrifice those for the crystal lovers. I do cut a lot of material, but not an intact crystal. I try to preserve them. And here we have again the chromium, the trivalent chromium, which is the cause of the color, but we do not have a lot of these yellow stains. So we have a more pure pink here in Katlang compared to the Europrato. Recently, people have found out that radiation treatment also produces some nice colors here. So if you get a little bit of a smutty or dirty orange color, then there's also a good chance that the material has been treated. However, radiation treatment does not produce pink color in these topazes. Afghanistan, also very close to Pakistan, is known for tourmaline, but not very well known for topaz. So there are just a couple of topaz locations that you can find in Afghanistan, and mostly you have this bluish material. Here we have one from the Mavi pegmatite, and this one is from the classical tourmaline locality Paprok, and in this case also a combination with tourmaline, which is also rather rare. Let's go to the Ukraine. So the Ukraine is known for the heliodors, of course. Everybody knows Ukraine, the Volodar Volyn is the place where you find these multi-kilogram gem quality etched heliodors. Some people might also know that these deposits were mined for quartz during the Soviet Union era because they needed the quartz because of its physical properties. It was a war relevant material. However, a couple of these cavities also contained topaz, and here we have a pegmatite that is 1.7 billion years old. So the potassium 40 had long time to irradiate the material, and therefore you have very intense orange colors, dark brown to orange. Light ones are called wine color, and very often we have bicolor, so we have blue and brown. The only thing that we know that does not work, and this is a little bit a way of identifying the material, if you heat those up, they will not turn blue. So this is the difference between the irradiated material where you have neutrons for a couple of hours compared to the potassium for a couple of million and billion of years. If you heat those up, they will not turn blue, they will just turn pale and start to degrade it at certain temperatures. So the color range can be from very intense orange to these, they call it cognac or wine color, bicolors, or even blue colors. So you see here in this crystal, part of this crystal is blue, and there are huge parts of the crystal that can be cut. And in the best of all cases, you get bicolors like this one, or you have really, like in the ametrine, split colors. Russia has one major occurrence, or had one major occurrence of topaz, Mokrusha mine in Murzinka in the Ural region. And this one has been famous for a long time for producing this wonderful blue topaz. Here we have a couple of species from the Natural History Museum in Vienna. Unfortunately, I do not have one of those. They can be rather large, 10 centimeters in size, but very often they're in the 1 to 3 centimeter size and nicely attached to matrix and this intense blue coloration. So nothing to be found there anymore. And actually, I do not know of too many cutstones that are actually have the pedigree of being from there. Maybe Peter Lickberg has some information on this. However, still as a mineral collector, I can admire these wonderful crystals here. Russia also, being a huge country, has other occurrences like on the other side of the country, we have Shelavagora or Adon Chilon, and they also have these hydrothermal quartzes, these hydrothermal topazes here from Sanarka or from Kamenka, which have pinkish, and in this case, in purplish colors. So this is now where the story begins with imperial topaz. There was a nice time when people were honoring their leaders of the country by giving them whatever they find. And if some gem material was found that was really nice and spectacular, it was presented to the Tsar of Russia. And therefore it was called an imperial variety. And this is the real, or at least to my knowledge, this is the real origin of the term imperial topaz. So imperial topaz are the Russian topazes, the hydrothermal topazes that share many, many properties with the ones of Katlang and Uropreto, like the hydrothermal occurrences, like the chromium being cause of the color. But you can not assign an imperial topaz by color alone. Where would you make the difference? Is it yellowish? Is it oranges? Is it red? Is it pink? There's a lot of discussion on in the trade and also in internet fora. I like to have a nice discussion on Facebook about topics like these, or tanzanite. Is it blue or is it not blue? Is it tanzanite? Is it zoisite? So imperial topaz, the name is derived from the Russian topaz varieties, which were pinkish, reddish to purplish. It has been transferred over the time to be Uropreto being the location that produces most of this material, that people associate the name imperial topaz with Uropreto. I would be more on the, let's say, on the chemical or on the crystallography side. I would say imperial topaz is fine for me for everything that has an hydrothermal growth, no matter what color it is. But again, this is a topic for lots and lots of discussion. So United States also has a couple of nice occurrences. We have the Maynard's claim in Utah, where we have these rhyolite-based topaz, small sizes, very often included with rhyolite or sand, so not a lot of cutting material here. But Zacatecas in Mexico, for example, is very similar. And a couple of decades ago, this was one of the major sources for these brownish-orange topazes. Another famous location is in California, the Little 3 mine, which produced wonderful bluish topazes. And we have also some small occurrences in Mason County in Texas, and of course, Colorado, where we have the Agnus Dei climb, a recent find, but also in all of these larger claims around Colorado, we can find also bicolor topaz, colorless and bluish color. Going to Africa, we start with Nigeria, a large producer of not only topaz, but many, many gems. You can find their colorless to light blue topaz. And this is a nice cut example, which for me as a cutter has some special meaning. It was the first gem, not the first gem that I cut, it would be wonderful, but it was the first gem that I sent to a competition, the United States Facetous Guild Masterclass. Well, and for being the first stone, it ended up being first place in this category. So I was really lucky with this one, and it's now in the collection of Somewhere in the Rainbow. So I'm very glad people can play with this gem, can touch it. Also, it might get some scratches. It has its 90, I don't remember the exact score, but it was something like 98%. So almost a perfect cut gem here. And when we talk about Africa, of course, we have to talk about Namibia. So this is my second largest piece we have here. This is a topaz, a couple of more topazes. In matrix, we have some smoky quartz, we have some amazonite. Before trimming, this piece weighed 25 kilograms. It's now down to about 20 kilograms. So this is more than 10 centimeters here, this topaz. And Namibia is one of the countries that produces a special kind of topaz. It has derived its own name. It's called the silver topaz because they're absolutely colorless and they have this silvery sheen like we have here in the top and in the bottom. And we have also some light blue coloration in some of the topazes. So again, a major producer of topaz specimens, but also topaz rough for cutting is Namibia. So this was just a quick walk through some places on Earth where you can find topaz and how they look like as specimens or as cut gems. And it wouldn't be me if I didn't have some nerd part in the talk. So the nerd part here is a little bit about analytical chemistry. Don't be afraid, I don't touch all these 4 topics that we've done FDIR spectroscopy, we've done Raman spectroscopy. What I like to do is laser ablation ICP-MS. For those who don't know what it is, we'll have a slide on this afterwards. And SAM, which is electron microscopy, scanning electron microscopy, coupled with an energy dispersive X-ray detector or wavelength dispersive X-ray detector. So these are wonderful for determining the chemistry in topaz. This is how it looks like. So you get some peaks and you get some element. We have oxygen, we have fluorine, we have aluminum, silicon, a little bit of potassium here. And with this wonderful technique, this electron dispersive X-ray spectroscopy, you can determine the content of fluorine versus the oxygen. And this is the first wonderful difference where you can differentiate different topaz localities and or at least the growth, if it's a hydrothermal growth or if it's pegmatite. And this gives you the content of fluorine, which is not easily accessible by many other techniques. However, I play a little bit more likely with laser ablation ICP-MS. So laser ablation is a system where you have a laser and you have a camera, you look at your sample and you shoot with a laser onto your sample. And then you make some nice explosions. So these explosions are very, very tiny. We are damaging the stone. Yes, that is true. But if you do it for a gemstone, for example, the girdle, you leave some spot of 10 to 50 micrometers diameter and a couple of micrometer steps. Without a loop, you're not able to see them. And if you want to remove them, that's polished within a couple of minutes. So this material that has been removed from the gem will be carried on with a carrier gas into an ICP-MS, inductively coupled plasma. What happens here, we disintegrate all these parcels of material that are coming through, and we create ions. So we create ions out of everything, and these ions are then analyzed in a mass spectrometer. Mass spectrometers are machines that separate ions by the mass over charge ratio, and they can count the number. So what you get is how many ions of what kind are in your sample. Sounds pretty easy, perfectly easy. In fact, it's a little bit tricky. However, what can we get for an information? You see here the periodic table of elements, and everything that's colored here can be measured by ICP-MS. It's just a couple of elements like the hydrogen, carbon, nitrogen, oxygen, fluorine. Unfortunately, chlorine sometimes cannot be measured, but everything else can be measured and can be measured very, very sensitively. So if we go down here to the rare earth elements, we have a detection limit of about 1 parts per trillion. The other ones parts per billion. So you might know parts per million, but this is another step and another step, parts per trillion. So this is almost nothing that you need to remove from your gem in order to detect it. And this is very important because there is this nice saying that I like to repeat in those cases that people claim, Mother Nature cooks in a dirty kitchen. And it means you have a little bit of everything in your surrounding. And your surrounding can be analyzed, and this gives you a clue where your gem has formed or where your mineral has formed. And this is very often important to find out where a gem was mined. You know, with all these politics going on, there are trade bans on some certain countries. You have to be sure that you have to be able to identify a source correctly. In topaz, I have to agree, it's not easy because there are so many sources available, but at least it gives you some ideas. Here's, for example, a map where we have sodium, magnesium, and a couple of other elements, and you see sodium is all the same in the samples tested here. Vanadium also the same. Did not test chromium in this case because it would be unfair. But we have iron here in 2 out of 5. We have cobalt, 2, maybe 3 out of 5, and we have some copper, which is in Brazil, no copper at all. But for example, here in Sandan's mine in Zimbabwe, this is a mine that produces the deepest blue topaz, deepest blue natural color. Has been abandoned for many, many years, but a couple of people have started mining there again 2 years ago, and they're finding again nice blue topaz. So far as I know, it's only specimen quality, no gem quality, but still nice to know. So by having these elements and the distribution of the elements, you can differentiate between a couple of different sources. Or the other extreme, you have 2 orange topazes, both have been seen here in this presentation, so you should know where they come from. But the question is it a cheap Pakistani topaz, for example, that has been color treated or something, or is it a valuable imperial topaz from Ouro Preto? So the price difference is huge for this material once they get larger than 2, 3, 4, like 10, 20 carats. This one is 60 carats, and this I don't remember exactly, but it's also 30 to 40 carats. So we're talking about some money here. So if we measure the chemistry with this laser ablation, we will find that here we have chromium as the source for the color, and here we have color centers. There is no chromium. And we can assign the origin here as being from Volodarsk or Koroshiv now, and this one is Ouro Preto. So this is a lot of money, still very good color, attractively colored specimen, but you are not sure if the color is stable. At the moment, I can say it's at least stable for 5, 6 years, as long that's the time that I have it in my collection now. But Pakistani material that is irradiated might have almost the same color, and that will fade within a couple of weeks or months. Synthetic topaz, something that I did not talk at all about. So we know for many, many gems, there are synthetic varieties available. Is synthetic topaz available? Most of you will say no. In fact, yes, it is available. However, synthesis of topaz has mostly been done for scientific purposes. So if you read the papers, then people are claiming we have a couple millimeters size, we have below 1 millimeter, and it's mostly topaz that has been transferred in some other minerals. I was lucky in 2019, and I found in Tucson a Russian vendor, and he had a drawer full of synthetic topaz. He said, keep one of those for me, I will come back later. Unfortunately, he did not keep any for me, but I found out who was the one guy who bought all, and he gave one of these pieces to me for analysis. And this is the results that we get from laser ablation ICP-MS. You see the number of elements that we're measuring and the concentrations. Each line is a sample. You don't have to read this, but I'll just give you a close in, and we have some synthetic topaz, the ones that here highlighted with the dark background. And you see, for example, the chromium, where we have something like 290, 100 ppm, depending. This is Ouro Preto material with the high amount of chromium. High amount, I'm talking about 100 ppm. And they have 2%, 1%, 2%. Huge amounts of chromium, huge amounts of iron. Not huge amounts, but still way higher than natural topaz here in manganese. So it is not possible to fool an analytical chemist with these topazes. They were the size of about centimeters. One gem was cut and sent to the GIA. Sorry, guys, you have been fooled there because the report that was returned back was natural topaz. If you don't know that you have to expect a synthetic topaz, you have no chance to identify it. But from the crystals, you see it because they have a coating that looks like, to me, I don't know how they did grow it, but to me it looks like they used a matrix similar to diamond growing. So synthetic topaz, yes, it is available, but it is no threat for the gem community because synthesizing the topaz does cost way more than buying some cheap colorless topaz rough. Well, finally, I have to acknowledge a couple of people, Dr. Peter Lickberg, for allowing me to use his slides, a couple of slides from him, and also for providing me with some of wonderfulest topaz specimens that I ever had. Stefan Kotlovsky, who also allowed me to use his photos, Anton Watzel Senior, who did a couple of the pictures, and Tony Gill also for his picture of the Sanarka topaz. And finally, I have to thank you all for staying with me, listening to me for that long time. I'm sorry, I always run out of time when talking about topaz. I could do this for a couple of hours more, but I tried to make it short, and I hope that I did not send too many people asleep now. And if you have any questions, I'll be here to answer them. Thank you.
Thank you. Anybody got any questions out there?
I've got a comment, not so much a question, about the Mazinka topaz. Now, in the Natural History Museum in London, they have several pieces that have been kept in the drawers in the dark for 100+ years. And these are sherry brown color. And apparently similar crystals from the time that were put on display have turned sky blue. So I obviously can't say that all of them came out of the ground as sherry brown and then changed in sunlight to the sky blue, but certainly some of them could well have come out as a different color and changed over time.
Yeah, I've heard the same thing, that they intensify the blue color when they're on display. I think if Peter is here, he could surely talk a little bit more on this.
Yes, I think Julian is mixing with ones from Volga River, which is very far east in Siberia. It's 3,400 kilometers to the east. So in Bancroft's book, he put the two together in the chapter, just to, I think, minimize the number of chapters, but it's completely different. You know, that's from West Coast.
My apologies, I think you're right.
To New Hampshire. But anyway, what I haven't really published too much is I've dug several pockets in Mursinka and Makrusha. I've been to Makrusha and the underground also. And what is there is that the topaz is blue. It can be almost colorless. It has a termination that's often champagne, and you've seen the morphology of them. The color and which part of the crystal will have which color depends on the morphology. And the center is also champagne colored. That champagne fades very quickly, so you get a blue crystal after a day out in the sunlight. If you keep that in the dark, you can still have the champagne core and termination, but the termination tends to fade very quickly. So the Mursinka and especially Makrusha mine, they're completely blue, but very rarely. So I think very few people have ever seen that champagne color in Mursinka ones. And this from Uralga River, Bolshovotsny range in Siberia, they are very, very strong brownish color, and they will fade quickly. So for instance, in Mining Museum in St. Petersburg, I think all of them have faded. And the British Museum have three. One they exchanged with the Sorbonne Museum, and they have it in the display, but they were very clever that they mounted the lights at that time on the outside, and the glass, the thick glass, takes away all the high energy, so that even though it's on display, it didn't lose its color. And the three ones that have covers in the British Museum in London, they still have very great color, but they should not be shown too often in the daylight, which is in there. And I can give you some more examples. For instance, the Ukrainian ones, Clemens here have shown very much. They have some of them. Clemens showed one photo that I took in one pocket, where you could see champagne, you could see bicolored. Many pieces in that pocket. There were not too much topaz, but they were colorless. And they were in fact parts within huge, up to meter or even more than a meter size pseudomorphs of topaz that was now sericite. And there were small bits and pieces of topaz in there. So the photo I took, there were pieces about this size. There were some larger, colorless, but they had a beautiful bicolor and very intense orange color. And some of the large ones in Volodarski you've seen. I will just show you, if you like to see a couple of what they look like when you find them. Does not look very pretty. So the crystal is here. I've cleaned off a little bit, but that's what they look like when you find them. So most of them are not clean at all. And you see, this is the matrix. So many pockets, they're not open. They're in fact very solid, hard that you have to mine. And this came from a pocket that was 23 meters deep from the top down. They had entered the pocket in the old days, but when the new mining company in the last decade went down 6 meters, they started finding topaz. And this came down from 50 meters below the tunnel level. And we found one there, 230 kilo, one topaz. I'll show you another one. They don't look very beautiful at all, but these are completely deep orange colored. And the deepest color is concentrated on the outer. So that is from the radiation, both from potassium 40 and other. There was quite a bit of radon when they opened some of the pockets. So there has been in the past, of course, 1.7 billion years ago, the radiation was much higher. And I will show you one more example just to see how ugly a topaz can look like when you find it. So you can only see from the morphology here that these are very nice topaz crystals. They have 3 millimeter albite cover, and the color inside here is deep orange. I don't want to take more time from you. I can show a couple of other things and tell about a couple of different deposits, but please ask questions to Clemens.
Thanks very much, Peter.
You're welcome.
Back to Clemens. So the one thing that I was surprised you did not mention, and I know you did a good job of covering a lot of things, but the stuff that came out of the Agnes State pocket in Colorado was amazing. I've got from Stephen Kotlowski's estate, I have 1,000 carat piece of rough, and I know he cut that showed at the Tucson show a 5,000 plus carat, or 3,000 plus anyway, and a 300 carat, and they both were deep peach color. They were very nice color, and there were some political interpersonal things going on with the people that that found it and other people. So there's been some rumors going around about the quality of the stones, but in truth, they've been exposed to light and they still maintain their color. So they don't fade like the ones from Pakistan tend to. So there were some very big, beautiful stones. And I think Stephen cut the biggest ones from that find.
Yeah, he did. The colors are very nice, and they very much resemble the Volodarsk material. So they're a bit lighter, they're a little bit peachy colored. I did not cover this. I had some slides on this in other talks that are more on minerals. However, there are a couple of personal things going on where I've had more than rumors, and this is why I did not want to touch this too much, this topic.
That's understood. Any other questions, Antoinette? I know you're chomping at the bit there.
I had a question.
Oh, good. Could you tell us your name, please?
Hi, I'm Richard Nahas in Ottawa.
Oh, you're Richard Nahas. Okay, good.
Thank you for an excellent presentation. Very interesting, very well presented. It's clear you love topaz. I was wondering about color fading and whether you can distinguish between the type of deposit or whether it's locality dependent.
Yeah, I've seen your question here in the chat. Is it true that all hydrothermal topaz is non-fading? Well, you have to differentiate between the causes of color. If you have a coloring element like chromium, this does not fade because the chromium is inside, and as long as it stays in the same surrounding, in the same place in the lattice, there is no reason to change the color. If you have something like a label color center, where you just have some distortion in the crystal lattice, that if it gets a little bit of energy, starts to move and can go back to natural position, then it will fade. So whenever you have irradiation, mostly the natural irradiation or the irradiation that has not had a long time to penetrate too deep into the material, then you have a good chance that these materials will erase or will fade with UV light. Also temperature would be the same. So you just need to put in some amount of energy. If we're talking about the hydrothermal occurrences, we have Kat Lang, which is purely colored, at least the good specimens are purely colored by chromium, so they do not fade. If we have the Brazilian ones, Ouro Preto, you have a mixture of color centers and the chromium. So the chromium will not fade, however, the color centers may fade. So I'm not aware of any fading when you put these material into UV light, but we know the temperature does the job, and if you heat them up to above 400 degrees, 400 to 500 degrees is what is typically done, you can remove the yellow coloration. So in fact, they are not color stable. However, you get an improvement in color, at least that's what most people think. The third occurrence, Russia, I'm not aware of anybody doing tests with this material because there's not a lot of them available. Many are in Russian museums. I know of a British collector who has a couple of small pieces, but he didn't want to give them to me for playing around so far, at least.
I have in my collection a stone that I cut about 16 carats, deep claret color with dark and intense red flashes, about 16 carats, and it was from a rough that was obviously frozen in matrix. It wasn't loose in a pocket, so I had to grind away matrix to get to the stone. But it was from central Mexico, and I don't have the exact address here with me. But I'd never heard of any from there before, and not too much since. It's apparently not a commonly known occurrence.
Is it brownish?
Pardon me?
Is it brownish color?
It's a reddish brown color, but with deep red flashes all through it.
Okay. So to my knowledge, a lot of material came from Zacatecas, which is a rhyolitic deposit that produces this more brown. So red flashes, I'm not aware of this, but maybe that's a better question for somebody who is in the trade.
Yeah. Are there any other questions?
Could I please ask one more question?
Absolutely.
Could I ask Peter a question? Hello, Peter. Lovely to see you.
Hi, Richard. Nice to see you too. Nice to see you all.
I just wanted to know if there's any information about the potential for any further exploration in Sanarka.
Yeah, I was there 2 years ago. So the original, in fact, this is interesting for Clemens also. The very first documented topaz from Sanarka arrived in Sweden 1850, and only 1853 Koksharov described topaz from there. Now that piece was exchanged with a German dealer who sold it to a German collector, and this was cut by Buzz Gray in California. And when that German collector 20 years ago was going to sell his collection, I just called him up and I got the two pieces I wanted from his collection. It was this Sanarka topaz, 37 carat plus carats, flawless. It's a beautiful, and now I say imperial topaz. It is orange, doesn't have the pink. And in fact, the old descriptions, they were everything from yellowish orange to pink to purplish. And one of the, in fact, it was the Kamenka River, it was gold washings, and one local collector had 2,000 crystals. Most of them were very small, so typically they would look like this. And there were gold washing both at Kamenka and Sanarka River. So at the Kamenka River, there are workings, and one friend in 1980s, he made a pit, so it's called after him, Igor Gurgov's pit. He made a small pit and fired the hydrothermal quartz veins, and he collected crystals to 3 centimeters. One friend 2 years ago, he found a very, very nice specimen with a quite large crystal, absolutely fabulous. So with Imperial Topaz, I agree with Clemens. Of course, Imperial Topaz should be, they're all hydrothermal, elongated. Of course, it's good they have good refractive index, and they're absolutely beautiful. This Sanarka one, which now is in my wife's collection, 37 karat, when you see that, you know immediately, this is not Brazil. You can see anyone with good eyes. Women have much better eye color resolution than we have, most men. I happen to have fairly good, so I have very easy to distinguish different localities for minerals or gems. It's very obvious. So for instance, the topaz on matrix with the smoky quartz that Clemens showed, I've seen thousands and thousands of topaz in Pakistan, even inside pockets I've seen. So it's very obvious radiated. There was also a bunch of barrels from Pakistan that were irradiated, and this you can see them from 50-meter distance. The color is not the same, and of course, if we would look at the spectrum, you would find some differences. Really, if the eye can distinguish, of course, with spectrometers, you would be able to. So I see we have George Rossman here also. This is something we should have a look at. I took 2 such barrels. Now I come out of topaz, but I took them. I work in the nuclear field, so I put them with very high resolution detectors underground, where a body counter, what you use to look for internal contamination. And I ran 3 cycles, several hours each measurement, and nothing had been activated in those. It means this was a linear accelerator they had used for this. This was not a SAC, which they usually do by reactors, which they bombard with neutrons, and then you can activate. For instance, I gave an example in the chat, topaz from Spitzkopje, where they irradiate 100 kilo or hundreds of kilos per year, and one reactor in St. Petersburg where they irradiate a couple of 100 kilos per year in the 90s, and they become fairly highly radioactive. And most of those they would keep underground for 10 years before even putting them to the market, so not just 1 year.
Wow.
So did
Sort
I
of
give
like the
enough?
radioactive glass.
I can give you a quiz if you would like. And now, where is this topaz from? I don't know if you can see it properly. Now the light is giving, it has a very strong orange color.
I would say it's from Peter's collection.
Yes, just came out of my pocket.
Must be Pakistan.
Well, it's Finland.
Really? That's nice.
Yeah. So Finland has blue in the same. There are different ages. There is Rapakivi granite, 1.63 billion years old. There are other younger pegmatites that also have topaz. And in those pegmatites, there are also in mesolithic pockets in the granites, there are also grayson. So grayson means on the top of the granite intrusion, you will have pegmatites within the granite going off into the country rock, and very, very high up, and maybe some spots on this intrusion might have grayson or late stage areas. And typical grayson will look like this. Plenty of small topaz. This is from a locality, Shelovagora in Transbaikal in Russia. This is a very, very old locality. So they are typically not for gem cutting, for grayson, but there's some 2-3 centimeters. But I just showed you that, and what Julian asked before about Mursinka. Here is a typical Mursinka that I use at my letter weight. People are laughing, but it's very, very good for pressing down the letters, you know. And that's all natural color. That's from my Krusha mine.
Oh.
Thank you so much, Peter.
You're most welcome.
And I feel very happy when I see people coming up with questions, because that's how we get the extra learning. Are there any more questions before I continue? I just had a little bit of housekeeping to do. Any other questions? Well, thank you much. Thank you very much, Clemens, for your contribution. Thank you, everybody, for coming. But I want to let you know. Go ahead.
I do have a question for Clemens.
Thank you, Antoinette.
And also for Peter and for George or anyone else here who collects topaz. If you have one example of a topaz that really excited you for whatever reason, First, do you? And if so, can you describe it? Come on, you must, Clemens.
Okay. I need to turn around to have a look at my topazes. Which is the one? I do like all of my topazes, so they are family. But maybe to highlight one piece and why I like it. This one is well, it is pinkish red Oropreto topaz. And what is so special about it? It is on matrix. You see, there's a nice quartz crystal, and you very rarely see these crystals on matrix. Mostly you have them either loose in the ground, or you find them with some ironstone where they're just embedded in. But this one is really, this is showing the hydrothermal growth. We have it attached to the quartz. So it is small topaz. It's about 3-4 centimeters, but it's so beautiful in terms of color and in terms of it is on matrix. So this is one of my very favorite ones.
Thank you. I love it. I think that's absolutely a fabulous specimen. I like everything about it. It's also my birthstone.
Yes.
I like red, in case anybody's wondering what to give me for the, well, I just had my, forget, I won't even mention which one, but I'm beyond 3/4 of a century. So before I hit the century mark, it'd be really great to have one that looked like that. No.
Really nice Oropreto to start with clarity and color. Just alone is very hard to get because the mine output has sort of been high graded for years by its owner. And so I'm really amazed at that specimen that Clemens has, especially since it's on a nicely formed quartz crystal. That's amazing. Never seen anything quite that good from Oropreto. In private hands, anyway.
And George?
So just to let you all know that we're going to take a break for a month. And that's partly because of the experience we had last year, since we meet on the last Sunday of the month, and that's after Christmas and just between New Year's. A lot of people don't want to be bothered. So what we're going to do is skip December this year and give you guys a break and start up again in January. And I'm sort of hoping that we can do it from Tucson, because I think Jolien's going to be there, and if we can manage that technologically, then we'll do it from Tucson. I hope to be at Tucson this year.
Well, assuming that they don't lock everything down again, but
yes,
hopefully
Jolien,
I'll be
you're
at Tucson.
absolutely right. Says the voice from the dark square.
Oh,
anyway, thank you, Jolien, for your technological expertise and your help to make this happen. Thank you, everyone, for attending, and we'll see you all in January.
Peter, can your son even hold that one?
Well, he just went down, but that is his favorite. You know, you asked about favorite topaz, and my son, he discovered that there was an empty cupboard where I used to have books that I had taken out, and he was only a year, 2 months old, and he started pulling things out of my collection. I had some big, heavy things far down in my display cases, and this was the topaz that he kept pulling it out of my collection and put it on his. I think I put it back in the collection about 10 times, but now it's his, because that's the one. And he really selected very well. He selected only nice pieces, you know, so all of them are now his.
Well, it's good to know the next generation is going to follow in your footsteps, obviously.
But if I would say my favorite, I saw a fabulous topaz that I couldn't buy for the reason that, oops, something happens.
I hear you.
Oh, you hear? I didn't lost you. I don't. Can you still see me?
Yes.
Yeah, we can.
Oh, something happened here. I don't know what, but anyway, I will show you if you can see this blue topaz.
Oh, another lovely one. Yes, exactly.
That is from the Ural Mountains, and this is a very old piece that came to in 1950s to Peter Bancroft. It was his favorite in his collection, and when he sold 53 pieces to Dave Wilbur, that was one of them. And then he visited me here in Luxembourg many years later and could review it. Again, he was so happy. He was already 94 at the time, and it was so nice to see him. Oh, that's my topaz, and I made pictures of him, playing around with it, and it was never pictured in any book at that time. So still
I
not.
remember the Detroit show when Peter introduced his new book at the time. And then I saw him at the booth for What's New in Tucson. And I didn't recognize him because he was so old and in a wheelchair, but he was still alive. I was stunned. Wow, geez, Peter's still going. Anyway.
99 years, 4 months. He passed on that day.
Well, I'm actually very pleased to see you have that, and you're curating it so well, Peter. Or your son might be if he gets his hand on it. So have a great Christmas, everybody, and we'll see you in January. And thank you all for your contributions and your interest and support.
And nice seeing you, George. It's been a long. Hello.
Thank you.
Yeah.
Thank you, everybody.
Thank you. Goodbye.
Bye-bye.
Thank you
Thanks,
all.
Clement.
Bye-bye.
Great presentation. Thank you.
Clemens, if you got a few seconds, if they don't cut us off, I can show you something that might be of interest to you.
Yeah, sure.
We're going to screen share here for a moment.
You're very lucky. I was just about to hit the button to kill
Okay.
it.
This is the electron source where the electron irradiated topaz was developed in Southern California. Charlie Key, as you mentioned, was bringing in the topaz, and they were telling the world that it was being irradiated by cobalt-60 by Marty Weld at his corporation in New Jersey. But in fact, it was actually being sent to San Diego, California, where Joe Borden was working with a company called IRT, Radiation Technology, that was practicing electron irradiation and trying various experiments. I got involved with Joe, and literally I worked with thousands of faceted samples and cut samples, trying various experiments to see how the electron irradiation could be optimized. And what you see in my share is the actual electron source at IRT. It's a big vacuum chamber with a tungsten filament inside. Electrons go shooting off to the right. And then after that, they go down this steel tube, which is a microwave cavity, where microwaves are injected into the cavity. And basically electrons surf the wave of the microwaves being accelerated to about 8 MeV energies. They go down the right to the tube, and then they come out the end right here. And there are steering magnets on the top, which raster the beam back and forth and up and down like an old cathode ray television set. And the samples are put in front of the beam to be irradiated. The voltage was kept below 9 million electron volts because at that energy, sodium would be activated. And it took 20 some days for it to cool down before they could release it. But this was literally how, at least in the US, the electron irradiation was developed, optimized, and processed for many years, a very well-kept secret, although ultimately the word got out and then everybody in the world jumped into it, in the US at least, with these electron irradiation facilities making the sky blue topaz. I also got involved with the irradiated topaz, which came out of Ouro Preto. And I came out of Sao Paulo, Brazil. Some people were moonlighting in the reactor, which was under good control normally, but some of the workers moonlighted and they were releasing radioactive topaz into the market. It was detected at the wholesale level, never released to the public, but I can assure you, the Brazilian government went ballistic when they heard about that. They got the military in to take control of the reactor, and every person that was wholesaling topaz bought radiation detecting equipment. So almost none of it ever made it into the consumer regime. It was all stopped at the wholesale level. And even that was very mildly radioactive, at least the stuff coming out of Brazil. It was activating the iron, the tungsten, and the manganese primarily as the inclusions in the topaz, not the topaz itself.
Wow.
Thank you for this information. It was wonderful.
Yeah.
It's
We should
always
talk separately sometime. I got a lot more I can tell you about.
that would really be a pleasure.
The highly respected gem company of Stearns in Rio de Janeiro was marketing very pale blue topaz irradiated as aquamarines until they got caught.
Oh.
That's when that was when it was still a new product. So,
Yeah, there was a lot of
Yeah.
cover-up going on, and unfortunately, in the early days, people were doing this not so much in an organized fashion, but simple people were coming into the reactors and trying their own little private experiments initially. But ultimately, that became under very strict control because of the industry was absolutely scared stiff that if it got radioactive material out into the public, it would destroy the industry. So there's just massive action was taken trying to control that, at least in the Americas.
Well, I do remember my father was, when he was doing appraising on the weekends, because he had the gemology and he had the instrumentation. And this woman who was the wife of someone with the State Department who bought this huge topaz in Brazil. And I have no sense of time, but I want to say it was the late 70s or early 80s. Maybe it was the mid 80s, but it wasn't later than the mid 80s. Anyway, she came in to have it appraised. And my dad took it, and he had just heard rumblings about material coming out of Brazil that was actually radioactive. And he had a Geiger counter. My father had everything. So he pulled the Geiger counter out, and the thing is going. He said, I don't think it's a good idea to wear this, particularly up around your neck where you're wearing it, because it was huge, big teardrop. And that was the first experience he had. And it was after that that the AGTA actually asked us to bring a Geiger counter with us to the show in Tucson. And we went through the show with the Geiger counter, the wholesale show, obviously. And there were several dealers who had material that set the Geiger counter going. And that was a little bit scary. Not as scary as when we came out and we're walking through one of the parking lots and we passed this truck, big truck with a drape on the back, and Dad had forgotten to turn off the Geiger counter and we're walking across, and you might hear a couple of little clicks. We get next to this truck and it's just like and we're like, oh my God. And my dad went over and he pulled the flap back, and the truck was filled with topaz, blue topaz, crystals, colorless topaz, just filled. And he said, Antoinette, get away from that truck. I mean, the feeling was, the Geiger counter was going so crazy, you just felt you were being exposed to incredible radiation. I don't know that we were, but it was scary. And but the trade did look into it, and they asked us to come back the following year, and there wasn't a single person at the AGTA show anyway that set off the Geiger counters. So we all relaxed, we took a deep breath, felt okay, people are taking this seriously. But that was the first time I ever had any firsthand experience with a quantity of radioactive material. But what you were just explaining, George, really kind of sets the time and the tone for me in terms of who was doing what and why.
Remember the year that you detected this?
I'm trying to, I want to say it was somewhere between the late 70s and the mid to late 80s, 1970s to 1980s. I don't remember, but everybody who knows me knows I have no sense of time. So I can't really tell you. I just remember it was Tucson. Dad was still alive. He's been gone for about 22 years now. So it was definitely before the last 22 years. Maybe it was 25 years ago. Maybe it was 30. It wasn't more than 30 years ago. I don't think. Could have been, actually. Anyway, why do you ask? I'll try to find out.
I'm just trying to place the time because I have dealt with radioactive quartz, radioactive spodumene, radioactive topaz back in the late 70s when all this concern really hit the fan, so to speak. And it was very, very quickly put down because governments took over. In some countries, the military come in to take control of the reactors, and massive concern in the industry made massive controls on the radiation sources, at least in the Americas.
That's what I was thinking. It was like late 70s maybe early 80s, but mid to late 70s could exactly have been the time frame. But I remember there was talk about some reactor or some people who had access to a reactor and didn't know what they were doing or some such thing. But the following year, it was not present in Tucson anyway, or at least people were hiding it if it was, because we tried to do it discreetly, but we didn't find what we had found just the year before. So thankfully, anyway.
Yeah. I think in the early days, it was England, it was Brazil, and it was Missouri that were doing the irradiations. Do you know of other ones, Peter, in the early days?
No, and I can confirm because it was the late 70s, because my mother had her 50th birthday in a few years into the 80s, and then it was already known for many years. So I went, she wanted a blow topaz for her 50th birthday, and I went to Norway for 3 weekends to find one for her, which I found a beautiful crystal blue, but I took an irradiated Brazilian one, a pebble that had been irradiated, but not too strongly. And I had that for many years in my collection already. So from, I think,
Cool down anyway.
yes, 78 something, and it was never irradiated so strongly. It wasn't it wasn't radioactive at all, I think. And so I cut that for my mother's 50th birthday.
Yeah.
You
Most
see
of the
that?
ones I encountered were actually very mild as an individual stone. Nothing was really super hot.
Yes.
Oh.
Like I wrote and I said the Namibian ones, they were super hot because of activated from, they put them right in the neutron beam from a reactor outside St. Petersburg, and they were very, very hot for a long time. So.
Well, that was the concern that we had in terms of what this woman's necklace, which was several years before we went to Tucson to do it. But it was one of the things that I'm finding, fortunately, in my own experience, is that when I first started in this field, there was so much going on. If you had knowledge and you had instrumentation and you knew what to look for and what to look out for, there was a lot of really bad stuff going on, and people tended to just cover their eyes. Nobody wanted to get involved and nobody wanted to do anything about it. And I have seen a major shift in the last couple of decades in terms of, maybe the trade is doing it for their own benefit, but whatever they're doing it for, actions are being taken and things are being disclosed and people are testing. And I think there's a much higher awareness and interest in really gems and jewelry, unlike almost any other product, carry an emotional connectedness that very few things do. And they get passed from generation to generation to generation. And they're beautiful, and it's something that nature creates, more or less. So I think it's really nice to see that the trade has stepped up and is taking a lot of steps to make sure that there is full disclosure and so on. And these Zoom sessions, what a wonderful opportunity for people to learn. I hope these go on after the pandemic is totally behind us and there are no more new strains of COVID and the rest of it. But I think that this has demonstrated more than anything else how dedicated and devoted real gem and jewelry lovers, mineralogists, gemologists, rock collectors, cutters, what they're sharing in this last year has been absolutely remarkable. And I applaud all of you.
Well, thank you, Antoinette.
I got two answers for you.
Your contribution.
Thank you.
At least you asked a question.
Well,
So,
it's almost midnight where I am now, and at this stage in life, I should have been in bed already an hour and a half to 2 hours ago.
Well, thank you for your dedication.
The conversation's been too great.
I got to share this. 1979.
We should end on a high note for sure.
Yes, that was one of my favorite interviews of all time. It was the most serious reporter interaction I've ever had in my life with any network or any TV or radio station. I gave the story. The office of the editorial group called me up to verify every single quote. The publication office called me up to verify every single quote. And this is what came out.
That was 1979?
Yes.
Wow! New lab process turns cheap gemstones into valuable jewels. Did everybody in the trade really love you after that, George?
No comment. At least I revealed what was going on, put it that way.
Right, right, exactly. Anyway, thank you. That was great.
Well,
Yeah,
thank you all.
I agree. This is a real benefit of these Zoom meetings, that you can share information around the world, and thankfully we have a lot of people who are willing to share the information. I prefer a Zoom meeting over in-person meeting, and this is the problem that we're facing. Again, we had 2 or 3 meetings
And
but at the moment everybody is going back to Zoom meetings, and it's not the same. Just talking into computers, you don't see the faces, you don't get the reactions back. So no offense taken to the Zoom meetings, but I really prefer in-person meetings.
oh, I think we all do. I'm so eager please let Tucson happen. Please let Vegas happen. Please let the gem shows in the world happen, because to be present, to see the stones, to touch them, to pick them up, to examine them yourself, and to be with your buddies who also get off on the same thing you do, which doesn't happen in my home. So, it's like, I would really love to be giving you a hug, Clemens and Ray and George and Peter for sure. I actually have hugged Peter in the last couple of years.
And Julian. And Julian.
Yeah, but it's really
Without Julian, we don't have a.
no. You're right, Clemens. There's no replacement for the in-person learning and the seeing and the handling things. But can you imagine where we would be this past 18 months or whatever it's been now without the Zooms? I mean, without these wonderful things. And at least we have had an opportunity to see the faces of people we know, love, and respect, and people we don't know, but we've now learned who they are and have a degree of respect. And won't it be wonderful to actually meet them face to face? Hopefully in Tucson, if not before, but I hope that Tucson, the next Tucson, when it happens, will be the biggest turnout in history.
Well, maybe I haven't talked to Ray about this yet. I don't know if you can hear me, because everyone's frozen. Can you hear me, Ray?
Yes, yeah.
Yeah, maybe what we can try to do for Tucson as a special event is have something where we have a mixed live and Zoom event, because
I would like
that would work really well. We'd have to consider the times though, because obviously in Tucson we would now be at a mid-afternoon time if we were doing it at our regular program time.
Right.
And so that might not be convenient for people who have, the day job working within Tucson. But let's think about that. I think. Oh, that's true. We could do that. So
we do it on a Sunday,
yes,
the last Sunday of the month of January, and that will be just fine at Tucson, I think.
Except for those who are working in the trade who have to do the shows on the Sunday, of course. But the thing is, the problem with Tucson is you never ever will find a time that everybody's happy with, because there's always so much going on. But yeah, Ray and I will talk about this later, and I think that it would be a wonderful thing if we could come up with something where you can either meet us in person or join on Zoom and still be part of it for that particular event.
It would be nice to have a GemQuest and GemDat gathering.
Well, if we know soon enough, we can plan. Even people who are working booths, if they know this thing is going to take place on a certain day at a certain time, even if it's during the week, the daytime when they should be at a booth, they can find someone to watch the booth for a couple of hours, to be there, to stand in for them. So maybe we can make it happen.
Yeah, I think Ray, you've got a date already, the last Sunday of January.
January. I don't have the date in front of me right now.
That's when it's
I'm in an information sparse environment here.
right. I know the AGA all-day conference is the first I think it's the first Wednesday. Wait a minute here. I do have it on my calendar.
And
And
should be Sunday.
hold on
Yeah,
a
so it'd be
minute.
Sunday, January the 30th, then it would be.
Yes.
And I'm assuming that it would probably be about then the same sort of time that we normally do it, Ray?
Right. Yeah. The AGTA show, I think, starts on the Friday. No, sorry. It starts in January. Wait a minute. Where are we? It must start. It either start. Oh, wait a minute. I'm in the wrong month. January. Right. I have a feeling that most of the shows will get underway on Monday, the 1st of February, and go for the next 10 days. Now, there are a couple of shows on the strip that open a couple of days before the AGTA, and a couple that open a day or two later and go a little longer. But somewhere between the 30th of January and February 10th, that block of time is always good because people come, and even if they're doing the AGTA show or exhibiting at the AGTA show, they stay a couple of days afterwards, just because there are other things going on in Tucson and other shows and dealers from other countries at some of the places along the strip. So, and they're still there for several days thereafter when the biggest shows have already closed. So that might be a time to look at, because we all stay for other things, but okay. All right.
All right, well, thank you, everybody. Thank you,
Thank
Ray,
you.
as always.
Thank you, Clemens. Thank you, Peter. Thank you,
Clemens.
Ray. Thank you, George. And thank you. Is it Jolian?
Jolien.
Jolian. Thank you. It was nice meeting you.
But hopefully we will see each other in Tucson, and
Right.
I look forward to that.
All right.
Okay, right. Well, this time I am going to hit the button to end
And
it all.
yeah.
I'm glad that we didn't, because that was a very, very good conversation. And thank you, George, for bringing that to the table as well. And see you all in Tucson, hopefully. Okay.
Yeah. Ciao,
Okay,
everybody.
Greetings from Jamaica all the way to Syria.
Bye.
safe.
all.
Stay safe.